Hi everyone, and welcome to our weekly AATRN seminar. The speaker today is Iolo Jones from Durham University, and he's going to tell us about new methods in diffusion geometry.
Cool. Okay. So thank you very much for having me. It's really nice to be here and to get to meet a load of you guys. So today I'm going to talk about diffusion geometry, which is something that I've been working on for a couple of years now. And I'm going to talk a bit about some new methods that are either recently published or hopefully going to be published quite soon. But today I want to focus the talk on giving an introduction to the general themes and ideas and what the point of diffusion geometry is and why you should care, and the sort of general background and intuition, and then at the end, in the last sort of 10 or 15 minutes, then rattle through a bunch of new stuff. So to give an overview of what this is and what it's about, I want to use this figure which shows 4 different geometric objects that are sort of geometrically related, yet they're kind of categorically quite different things. So in the top left-hand corner, this is a manifold, which is a super well understood and studied object where we have a ton of theory about how to quantify what the shape is and its geometry and its topology and all of this kind of thing. In the bottom left, this is a sample of data from the manifold. So it's not a manifold, it's a finite set. It's a very different sort of thing. And yet there's a sort of statistical question implied here, which is that you can see enough of the shape of the manifold in just these finite data points that you can ask, to what extent can the geometry that we have in the true manifold be estimated from it when we only have a few points? And given that there's enough data here to see really what the shape of the manifold is, you would think that you can really build quite a complete theory, even like the sort of the tensors and the Hessian and the Riemann curvature tensor and all of this sort of stuff. You sort of ought to be able to see it given enough data like this. Now in the top right, this is a bit more of an interesting case. This is a probability density function. So this is a function from R2 to R. It's no longer a manifold, and yet when we plot it like this, you can see clearly it has a kind of shape to it, and it has a kind of shape that's related to the manifold that it's next to. It maybe represents like a manifold with noise added. And I think this is really interesting because even though it isn't a manifold, you can still clearly see a load of the stuff there. And so you can ask, to what extent are the geometric features that we see on manifolds perhaps a special case of a more general thing that exists for probability spaces? And then if you believe that, then there's the sort of corresponding statistical question of if you have noise here, or sorry, if you have data here, then can you see the geometry statistically? So the point of diffusion geometry in this context is to kind of complete the square of stuff. So it's to take theoretically geometry that only exists on manifolds and to generalize it to probability spaces. And statistically, computationally, it's to do the bottom row. How can we take data from a manifold or from a space and estimate the underlying properties of the space that it comes from? That's the goal here. So concretely, there are kind of 2 questions that come out of it. There's the theoretical question of how much of the Riemannian geometry of a manifold is a special case of the Riemannian geometry of a probability space, whatever that means. And then secondly, how can we estimate that stuff? How can the geometry of manifolds and probability spaces be estimated from a finite sample? So regardless of what the theory is in the first question, how can you estimate it statistically? The point of diffusion geometry is to extend Riemannian geometry sufficiently that you can apply it to probability spaces, and then crucially to do so in a way that lets you compute with it. Before I get into too much detail on that, though, I wanted to address this question about the manifold hypothesis, which is something that you see come up a lot when people talk about applying geometry and topology in practice, when we have these sorts of classical theories that apply on manifolds and we want to apply them to data. So what I want to distinguish here is between the manifold hypothesis that says your data actually lie on a manifold and the low-dimensional hypothesis that says that your data has some intrinsic low-dimensional structure, even if it's high-dimensional. And I think this is really important because I think these 2 ideas often get confused when they're actually completely different. So if you have an example here, like this data on the left is on a manifold. It's a circle, it's one-dimensional everywhere, it has a tangent bundle, it has all the stuff that manifolds have. if you look in the middle here, this is two circles, but they intersect. They intersect here in a kind of degenerate point where you have a kind of branching feature. And so this thing in the middle isn't a manifold, even if it's low dimensional. The fact that it has this intersection point is something that manifolds can't. And for a sort of similar defect, if you look at the data on the right-hand side, it's kind of 1D, and on the left-hand side, it's kind of 2D. So it sort of has a low dimension, but that dimension changes. And again, manifolds don't have that property. So if you want to say that something's a manifold, it's not really a matter of saying that it's low dimensional. That kind of doesn't matter because manifolds can be high dimensional. What it is a statement about the topological regularity that has to be uniform enough. So manifolds must never have branching points or singularities, and they must also never have a variable dimension. And this is quite important practically because, like, if you want to apply Riemannian geometry methods, like say if you want to find a tangent space with local PCA or something like that, that only makes sense if you genuinely have a manifold. If you are in either of these two scenarios, then you'll just get nonsense from that because you don't have the basic structure that you need in order to apply manifold-specific methods. So, you know, I think part of the reason these things can get confused is because they both somehow relate to like local dimensionality. Like, for example, you often hear people say about like the space of images. If you take an image, there are only certain ways in which you can deform it, and therefore it kind of has a local low dimensional structure. That's perfectly true, but I think you can then like accidentally come to the wrong conclusion that therefore it's a manifold, when actually that's a sort of unrelated thing, which is to do with, does it never have branching? Does it never change its dimension? So that's the context, and I think is sort of a motivation for why being able to generalize geometry beyond manifolds is super important, because most data, if it's high dimensional, may have low dimensional structure, but in general, you can't rule out these kind of defects without really good evidence. That in general, it's really hard to have. So today I'm going to talk about diffusion as a kind of general thing, diffusion on manifolds, diffusion more generally, and concretely why it's a geometric thing. So the point of diffusion geometry, the answer to the questions I was posing earlier, is to use diffusion as a kind of structural idea for generalizing the geometry and computing the geometry. So I'm going to talk about what diffusion is. I'm then going to talk about how we can use it as an ingredient to do Riemannian geometry more generally. And then I'm going to touch on at the end a bunch of new methods, some of which are already online and some of which are still kind of works in progress. Okay. So I think that the sort of best place to start with talking about diffusion is the sort of simplest example, which is how diffusion works in Euclidean space. So we can define this heat kernel PT, which is the sort of familiar Gaussian exponential kernel. And what you can think of this as measuring is how much heat would flow from a point X. If it started at a point X for T time, what the kind of shape of the heat distribution would be. So when time tends to 0, you've just got like a Dirac delta, and then when time increases, it kind of flows out smoothly like this. And crucially, we can use this to define a heat diffusion operator, PT, capital PT here, via convolution with the kernel, and that basically represents if f, your function, is like a distribution of heat at time 0, how that distribution of heat would evolve in time if it were to like flow forwards. And we can formalize this via the heat equation, which is, I'm sure you've all very familiar with, where you start with an initial condition f, and then you flow it forwards in time. And the solution to that is given by this operator PT. So when I say operator, it's a linear operator on the function space. So f is a function, and that maps to PT of f, and that's a linear map. This is where things start getting more geometric, and this is a really important detail, is that PT has this property that if you differentiate it at time 0, you get minus the Laplacian, where the derivative's in the sort of L2 sense. So you can think of the Laplacian as being like the derivative of the heat flow. And this is important because the Laplacian is going to show up a lot later geometrically. And so it relates to the geometry because the heat flow is generated by the Laplacian in this sense. And this is really a very general phenomenon, because if you have a manifold, the Laplacian exists more generally on manifolds. That defines its own heat equation, and that defines its own heat operator PT. So concretely, what that might look like is you could have a function f here that's sort of hot here and then cold everywhere else at time 0. And then as time evolves, 1, 5, 20, that kind of flows outwards. And the crucial reason why this matters is that the way in which it flows is related deeply to the geometry of the space that you're on. So the heat here flows to its neighbors. And so a lot about the geometry of the spaces is sort of captured by the behavior of the flow. Okay, so what concretely is that relationship with geometry? So there is this very clear connection. I think the best way to think about it is that geometry on manifolds we describe using the language of differential forms and vector fields, differential forms and the metric on them specifically. The sort of really fundamental thing that lets us make this bridge is that we have this identity called the Carré-Duchamp identity that relates on the left-hand side, this is the metric of df and dh, the one forms, with on the right-hand side, the Laplacian, where the Laplacian's the derivative of the heat diffusion. So the sort of the big idea here is that we want to define geometry on other spaces. We can do that by generalizing the heat diffusion and using the Carré-Duchamp identity as like a definition for all of that. So if you look at the right-hand side, that's analysis, basically. It's functions and Markov diffusion through the Laplacian delta. That's just a statement about the diffusion. And on the left-hand side, you have geometry and topology and all the stuff that you'd like to be able to define expressed through the metric and the forms. So by exploiting this relationship, we can use heat diffusion as a general framework for measuring and defining and computing geometry by plugging stuff into the right-hand side of this and using it to get the stuff on the left. So to talk about why that's a bit more general, why it is that we can use this to generalize beyond manifolds, we can think about the heat diffusion operator PT on a manifold as a special case of something more general, which is a Markov diffusion operator. So we call PT a MDO, Markov diffusion operator. Delta is its infinitesimal generator, which means basically that it satisfies that derivative property that when you differentiate PT, you get delta. But there's sort of the reason why this matters is that Markov diffusion operators are way more general than the sort of stuff you get on manifolds. So you can have probability densities or graphs or stratified spaces or fractals or all of these things that are not manifold-like, but where you can still have Markov processes. So to give some concrete examples, I mean, a simple deviation from a manifold is if you have a manifold with a density on it Q, then we get this weighted diffusion operator, PT of F, given by basically the same formula, but now we're integrating also with this different measure Q. So that's a different diffusion operator, and it gives us a different Laplacian, where that Laplacian, you can see Q showing up in there. So if you were just in the usual manifold case where Q is like a uniform distribution, then Q would be constant, grad Q would vanish, and so this would just be the normal Laplacian. But if we've got this different weighting, then we get this slightly different thing. But all of these are kind of really like tiny examples of the general case, where the general case is if you have a Markov process on a measurable space, then the expectation of F of your Markov process defines the diffusion operator. So if T is 0, the process has not gone anywhere, and the longer T goes, the more your function is kind of diffused out. So this is really the general case, and then you can think of the manifold one as being a special case of this, where your process is Brownian motion. So to sort of visualize this is like the circle example I gave you before, although this is like a noisy circle now. So it's now a slightly different sort of objects, but the point of this is to show that the heat flow process still makes complete sense, and it does what you'd want it to. Like you have the same thing here, and it flows over time. And the point of this is that this space looks like a circle, and you can quantify the fact that these spaces are close because the heat flows are close. And so if your geometry is constructed out of heat flow, then you can compare manifolds like the circle with a non-manifold like this and measure the fact that geometrically they're similar objects. But we can also do like far more general things, like this kind of figure 8 shape. You've got a yellow bit, and then it kind of flows out sort of in the way that you'd hope it would, even though you're not on a manifold. I don't know what this is, like the same thing, but with a kind of splodge here. And you can see, again, over time, it's like the the splodge kind of cools down this bit. So the point is that the heat flow dynamics are something that are general and that you can sort of think about geometrically. Okay, so that's the setup. So how do we actually define all of this stuff? So like I said before, the key ingredient is that Carré-Duchamp identity that bridges between the diffusion stuff and the geometry stuff. So we want to try and formalize this in the general setting. The way we do it is by defining the Carré-Duchamp operator. So if L is the generator of a Markov diffusion operator, we can define this bilinear map, which is called the Carré-Duchamp operator, basically by plugging in that formula that we saw before, where the key motivating example is that when you're on a manifold, if you have the Laplacian, then what you get from this is the metric. So this is a way of basically building a Riemannian metric out of a Markov process. The general setup that I'm using here is this thing called the Markov triple, which is a sort of classical thing in probability theory, which is really like the really bare bones basic ingredients that you need to do geometry generally. So we're going to have a measurable space E. So this is instead of a manifold, we're just on a measure space. We're going to have an algebra of functions, real valued bounded functions. So this is instead of like C infinity of M smooth functions, we're swapping it out for some generic A. And then we're going to have a symmetric bilinear map gamma, which is the Carré-Duchamp, and this is going to play the role of the metric. So gamma maps a pair of functions to another function where that function is behaving like g of df dh. So this is the general setup that we want and is what we're going to use as the sort of the ingredients for it. And again, the motivating example being if you've got a compact manifold M with metric G, volume, like Riemannian volume form dx, gamma of f and h given by the metric, then this is a Markov triple. So this is the thing that we're trying to generalize. Where sort of to spell it out some more, so manifold becomes measure space, volume form becomes measure, the smooth functions become this algebra A, the heat diffusion on the manifold becomes a general Markov semigroup, the Laplacian becomes whatever the generator of that semigroup was, and the metric becomes the Carré-Duchamp that we can build through it. So concretely, how can we define this? So on a manifold, we use the cotangent bundle and we use the metric as a inner product on the tangent spaces and all of this like manifold specific stuff that in general we don't have access to. So in order to define them, we want to basically make these two observations. One is that an arbitrary, so thinking about one forms, an arbitrary one form you can write as linear combinations of terms like this, like pairs f and h that become f dh one forms. And if you take the span of them, that gives you all of the one forms. And then the second thing is that we have this formula for the metric. We know how to write the inner product of one forms in terms of gamma. So we want to take a Carré-Duchamp gamma and a function space A, and we're going to define forms basically in the same way that enforces that stuff to be true. So we start with A. Gamma is a bilinear map on A. We're then going to think about one forms basically as being like the tensor pairs of functions. So these are going to play the role of FDH in the space of one forms, but we're going to construct them out of tensor products of f and h. And the really crucial thing that makes this stuff behave geometrically is that we know what the inner product should be in order for this to be a sort of geometric thing. So the inner product of f dh and f prime dh prime is given by this formula here, which if you were on a manifold would be the appropriate Riemannian inner product on one forms. So we'd like that to be the inner product, but it could be degenerate. So there could be stuff in the kernel of it. So at the moment, we know it's only positive semi-definite. To make it positive definite, we're basically just going to quotient the space by the kernel. So if we make D be the space of the subspace of tensor pairs that have zero norm, we can define the space of differential one forms to be this quotient. So we're going to quotient the tensor pairs by D, and the bilinear form now descends to an inner product, and now we basically have one forms in a more general case. And to sort of signal that we've got there, we're going to denote the equivalence classes that we have by FDH like this, and then this is then the definition we have. And then something similar for K-forms that I'm not going to show here. So overall, this is basically the idea of this is like, we wanted to find this structure, we strip away everything except a couple of basic ingredients in terms of diffusion, and then we can build everything back up again using only those things. So within this framework, we get to then define a ton of other stuff. So for example, the Riemannian metric, we can plug in the formula that you want to have. So G of FDH, F prime DH prime is, you sort of factor it out, you plug in gamma, and then you have the formula for the metric. Or if you want to take the exterior derivative, this kind of seems tautologist mapping like F to DF, but DF here means 1 tensor F. So it's kind of just a formal thing that you're tensoring on the left with 1. But crucially, because we've got this inner product space where the inner product space like treats these things like 1 forms, we then you then get like access to it as though it's a form. Okay, so I'm going to touch very briefly later on how you actually compute stuff, but for now, just show a bunch of like images of how it works in practice. So here we have a space, the one I showed earlier, it's not a manifold because of the kind of dimensionality failure, but we can still define forms on it. So here, these are 1 forms. So concretely, what we're looking at here are the dual vector fields of 1 forms. So a 1 form you can dualize to a vector field. As a vector field, it can act on functions, and that lets you basically visualize it as a vector field. So here we've got alpha and beta are 2 1 forms on this space. And we can compute the Riemannian metric, G of alpha alpha measures here. So here red is positive and blue is negative. So this is kind of measuring the support of where alpha is. Or if we compute G of alpha beta, you can see that this varies. So like on the right-hand side, they're both going uphill, and so their inner product is positive. But then on the left, they go the other way. Alpha's coming back down while beta comes up, and so they're unaligned locally there. And so the Riemannian metric of alpha and beta is negative here. The point of showing this is like, this is clearly not a manifold, and yet we still get exactly the behavior you'd want. As a similar example, you can take F. F is a function, it's got negative bits here and positive bits here, and we can compute its exterior derivative. So here df is arrows going everywhere. You can see it's kind of 0 at the maxima and minima like you'd want, but in the bits in between, it's kind of flowing uphill along the kind of along the like locally low dimensional bit. It's kind of curving around there towards the maximum of F. As well as a bunch of other stuff that I'm not going to show images of all of these things, but we can do the derivative and co-differential. We can take products, so the wedge product and the interior product. We can compute Lie derivatives and the connection. I think I've got a picture of this later. The Hodge-Laplacian is important, and I'll come back to it. And the Riemann curvature and the Hessian and a bunch of other stuff. So it's not really completely everything that you get in Riemannian geometry, but it really is almost all of it. We can put in this more general setting and then compute stuff with. So the reason I've emphasized the Hodge-Laplacian is because if you care about the like topological data analysis question of like where are there cohomology classes in your data, one way to access that through the geometry is to look at the Hodge-Laplacian, which is a operator from k-forms to k-forms, and it has this property that the kernel of the Hodge-Laplacian is the cohomology of the space. So this thing alpha that I showed you before is really a harmonic form. So it's a 1 form alpha that's in the de Rham cohomology class of this space. And so it's like very concretely measuring the fact that there's a hole in the data here via measuring it through the harmonic form alpha that we can then sort of localize via the metric if you want to see like a sort of indicator function for concretely where the cohomology class is. This is one more demo. I mean, I'm not going to talk about this in a ton of detail, but we've got vector fields x and y, and then we can compute the Levi-Civita connection of them. So I guess like the point of this is just that there's loads of stuff you can do, and like there's all of this theory in Riemannian geometry that we can now like directly port over and do on data at all, do it more generally than manifolds, do it efficiently, and do it robustly, which are all sort of really key things. So I do want to touch very briefly on the computational aspects of this, although not in a ton of detail. This is more going to be a kind of very brief overview. So as I've kind of been emphasizing, the key thing is the Laplacian and how that gives you the carré de Champ, and the carré de Champ gives you everything. So the reason this is a nice recipe computationally is because there are loads and loads of really good tools for computing the Laplacian in different discrete contexts. So I'm using the diffusion maps Laplacian that uses the heat kernel to try and get at the Laplacian there. And the key thing is it's really robust to noise. So a load of the kind of good statistical properties that we see from these methods are sort of inherited from the fact that the diffusion maps Laplacian is really good. But you could use a bunch of other stuff that I haven't tried, but would be nice. So say like the combinatorial Laplacian on a graph, if you plug that in, you would get like a discrete model of Riemannian geometry on a graph, which would be nice because that doesn't exist already. Or generators of other kind of things. So you can think of this generally as like a recipe for how you turn Laplacians into differential geometry, Riemannian geometry. So concretely what that recipe is we basically want to follow what the definition of one form says, more or less. So we have functions A, we take tensor pairs of them, and then we quotient out by the zero norm things. So concretely, we can sort of do that directly on the data. So we want to take a function basis fi. So the sort of obvious thing to try would be like if you've got n points in a point cloud, then the standard basis for functions is to identify the function space with Rn. So the basis elements there, like the ith basis element refers to the function that is 1 on the ith vertex and 0 on the others. So that's one example of a function basis that you could take, but you could also take other ones. And I'm taking a different one actually in this, but there are sort of, it's slightly arbitrary. The point is just that you pick any basis of your function space. You then want to take the tensor product as, following the definition. So if you have n things in your function space, you have n squared elements in your tensor product. And then the sort of the magic step that brings in the diffusion and makes all of this stuff work is computing the inner products of things. So if we compute the Gram matrix of a tensor pair ij with a different tensor pair I prime j prime, we can evaluate that using the Carré-Deschamps, and we can evaluate the Carré-Deschamps using the Laplacian, and that's the thing that we've estimated. So you start with the Laplacian, you turn it into a Carré-Deschamps, you can then integrate it, and we can get this sort of Gram matrix here, and that lets us concretely realize all of these things in the discrete setting. There's, of course, this issue about like degeneracy. So for example, if you have a constant function f, then df is going to be 0. So we need to mod out by these degenerate things. And concretely, what this basically means is that you diagonalize the Gram matrix, and then the degenerate things show up as like 0 eigenvalues. And then if you just project onto a positive definite subspace, then you get access to that. Okay, so I'm now going to show a bunch of sort of practice. Oh, are there questions in the chat?
Yes, we do have a question in the chat window from Vladimir. Where does the inner product on A come from? Could you maybe review?
So this is the inner product on this space here, the space of one forms. And this is the inner product that we defined to be like this. So do you mean like where does that formula come from? Or okay, if you do mean that, it's because that's the one that you would get in Riemannian geometry. Like if you plugged in
yeah, so but if you, sorry, I apologize. If you start with the cloud point, where does your inner product come from, really?
Yeah, that again, sorry, if you start with what?
Like you showed examples where you clearly treat point clouds, right?
Mm-hmm.
So if you start with point cloud, how do you come up with your inner product?
So you start by estimating the Laplacian via diffusion maps or some other method. We can then get the...
Okay, you do diffusion maps on metric graphs, correct?
Yes, you could think of it like that on a metric graph. But yeah, you do diffusion maps, you get L. You can use L in this formula to get gamma, the Carré-Deschamps.
Okay, so it really all comes from the metric graph. Then you just use diffusion map, the classical one on the graphs, and then you just push it to the one forms. Okay.
Exactly. Yeah. So.
And then we have another question from in the chat window. Can you use these methods if you don't have a point cloud? What if you only have a symmetric matrix that represents a metric between your data? Would you need to find some embedding of your data as a point cloud in some other metric space?
Basically, no, although there are sort of engineering reasons why having an embedding is useful that I would be happy to talk to you about if it's something that you're interested in. But so yeah, like concretely, the way I'm actually computing this is using a different basis for like the first factor and for the second factor. And if you have an embedding, you can get you get better performance basically. So if you only have like a distances matrix, oh, sorry, you were saying, do you say a symmetric matrix that represents the Laplacian or the distances or the metric? What was?
Yeah, distance matrix, basically, that represents a metric between your data.
Okay. Yeah, no, in that case, you can do this all fine. Yeah, it just, so most of the plots that are in this slideshow are from the first paper where I was only using eigenfunctions of the Laplacian, which are an intrinsic thing that you can get just from the distances matrix. Some of the new work that is featured at the end of this is changing that up to use an embedding, which does work better because if you only have a distances matrix, that's way less information than if you use the actual embedding coordinates that you started with. So you can do it just with a distances matrix, and everything in this slideshow so far is just with that. But if you also have an embedding, that's particularly good.
Thank you.
Is that all right?
Yeah.
Okay. Okay, so I want to show a couple of the practical aspects of this. So one is complexity that I've alluded to before. So in the sort of TDA context, a relevant question is how can you compute the kind of holes in it? And like I was saying, the way in diffusion geometry to do that is to diagonalize the Hodge Laplacian, which is like the analog of trying to do persistent homology. So to give a sort of complexity comparison there, this is doing that on a torus compared against RIPSA, which is a sort of highly optimized way of doing persistent homology. And you can see that, so the x-axis here is the number of data, the y-axis is on a log axis, the compute time in seconds. And so going via these diffusion geometry methods is like orders of magnitude quicker because you're, well, for lots of reasons that are kind of hard to explain briefly now, but exploiting these sort of geometric structures gives you like very good computational performance. So doing even like 12,000 points, I think only takes about 6 seconds in this regime. Whereas doing that, computing H1 in RIPSA with 12,000 points would be like, well, within the context of this test would have taken a couple of hours, which is why I only stopped there. Okay, I now want to show a couple of different new computational results that are not yet published, which is why the figures from now on are not going to look as good. But there are a few different things that we can do to get extra computational tools out of this. And the point of this is like partly to preview these other things, but mainly to show that if you have access to all of the Riemannian geometry toolbox, then there's like a phenomenal amount of like methods in there that you can kind of directly access. So one of these is computing geodesic distances, which is like the intrinsic distances within a space. This matters if you want to do like, say, intrinsic persistent homology, where you would want to, measure the size of features within the space itself and not necessarily care about their embedding. That would be interesting to try with this sort of thing. You could also do geometric statistics like the Frechet mean and variance and stuff like this, which normally you only do on a manifold that you know, and here you could do on not a manifold that you don't know. So I think there's a lot of kind of interesting potential with having geodesic distances via this. Taking it a bit further, you can explicitly compute geodesic curves. So if you take any pair of points, then you can realize the actual particular geodesic path that you would take through the data in order to realize that distance, which we can do between arbitrary pairs of points. Where again, the sort of the underlying thing that makes all of this work being that the Carré-Duchamp is like such a strong topological, like geometric constraint locally that you can get access to everything that the metric can see. So geodesics in particular we can do. This is as I kind of spoke briefly earlier about if you want to do TDA and you want to find harmonic forms. We can go a step further from that and find circular coordinates for those harmonic forms, which I think is, has a bunch of applications where you would want to measure explicitly how far around a particular hole or feature you are. So here on the torus, for example, we diagonalize the Hodge-Laplacian and we find there are two harmonic forms, one for the cohomology that goes to like that, and then one for the little one that goes within it. So we get these two harmonic forms that measure that, but then we can turn them into these circular coordinates. Okay, so that's some stuff from new work that is like still in progress. Some other sort of demo applications for this. This is from a paper that I did in the autumn, which is specifically addressing if you're in this very special case, you have a manifold, what's the extra stuff that you can do there? One of the things is measuring the dimension everywhere. So because the Carré-Deschamps is giving you like the metric tensor, the rank of the metric tensor is the dimension of the space, basically. So if we have something with variable dimension or something with boundaries or corners, then we can measure those dimensions locally by diagonalizing the metric everywhere and using the eigenvalues of that to tell you what the local dimension is. So here, for example, like the Swiss roll is 2D, but it has this kind of 1D boundary at the edge, and then it has these corners where you've got a kind of you've got a hard 0-dimensional corner there. So I think this is interesting in general. And if you want to get a global dimension estimate, you can just average over the whole space. And then what I showed in that paper is that doing this is like a super robust way of getting a global dimension estimate. Or a similar thing is curvature. So these are the scalar curvatures, but you can also get the Riemann and Ricci curvatures by using some kind of classical differential geometry methods with the Carré-Deschamps and these diffusion geometry things using the Hessian. You can use them to get the second fundamental form, and from that you can get all of these things. So the scalar curvature of a hyperboloid is kind of negative everywhere, particularly in the middle. This is a kind of apple shape, so it's like positive everywhere, and then it dents in and becomes negative, and then bottoms out and becomes positive again. So this is the sort of like correct scalar curvature behavior that you'd want. And then also on the Swiss roll, which is like the sort of famous example of a like curved space that isn't actually curved in the sense of scalar curvature, which we're kind of correctly estimating to be 0. I've alluded quite a lot to robustness, so I just want to quickly show this figure as like a demo of, in general, why all of these methods are robust by just focusing particularly on the example of scalar curvature on the torus. So here, this is a really dense one. This is 3,000 points with no noise. So it's you can sort of really see exactly what the shape is. And when we compute scalar curvature, we get a super tight estimate of what the true scalar curvature should be. But crucially, and this is where like diffusion maps is really important, is because it's such a robust tool. When we start making the data more sparse and adding noise in, which we do every step here, you can see that we're still getting like pretty much bang on what you'd want with, with this sort of appropriate amount of noise in. So 2,000 points with quite a bit of standard deviation of noise, and then 600 points with even more noise again. Even in this sort of super degenerate scenario, we're still kind of seeing what you would hope to see. Okay, that's all I have to show you today. I feel like I've sort of rattled through a few examples at the end, so I'm sorry that wasn't very much explanation of what they are. I mean, hopefully within like a couple of weeks, I'll be able to explain it a bit better. But for me, what I think is exciting about this personally is that like these topics around Riemannian geometry and differential geometry, people have done for hundreds of years, and there are tons of really good methods there that people really understand, and there's this very rich theory. So being able to apply that directly to data, I think, has a ton of potential in all sorts of different ways. So I'm hoping to carry on exploring that a bit, but I hope to have given you a bit of a like oversight of the sort of basic ideas here. And yeah, I hope you enjoyed, and I would love to take any questions. So thank you for listening.
Thank you. So actually, before questions, I would just ask everyone to unmute themselves for a little round of applause for our speaker. We do that all the time. And now, please, questions.
Shall I unshare my...
No, I think you can, if there are questions regarding the talk, it might be useful to still have the slides visible. Feel free to...
Wait, can I just say, or like,
Yeah,
do other
absolutely.
people take
Yeah, I wanted to
precedence?
encourage people to just ask or raise their hands, whatever they feel most comfortable with.
Okay. Firstly, thanks for the great talk. Always nice to hear about exciting developments in diffusion geometry. My question is about suppose you're computing the basis for Hodge Laplacian. No. I mean not Hodge Laplacian, the Hodge basis of cohomology. And now suppose you're operating in D dimension and you're doing it for HK. And now you have D and K that determine your computation. So now my question is, how does the computation times scale? Like it's like an big O notation in D and K. So
Yeah,
D can be, maybe there's a big D and small d and K, where big D is ambient dimension, small d is intrinsic dimension, and K is homological dimension.
Yeah, good question. Okay, so I'm going to give the answer that will be like what's in the current paper when it's done, which is about reworking the way that stuff is computed. But the complexity is, it doesn't depend on the intrinsic dimension just because you don't know what that is and it might vary. But as a function of D, the ambient dimension, and N and K, it's going to be it's sort of roughly speaking is N the dimension of the spaces is n d to the k. So if you want to diagonalize that, then it's a n d to the k by n d to the k matrix. So supposing that diagonalizing the matrix is cubic, then it's n cubed d to the 3k. So it's the homological rank is decoupled from n, which is why it's more efficient than persistent homology.
So what was the final answer again?
So assuming it's cubic to diagonalize a matrix, then it's n cubed d to the 3k.
D to the 3 and then linear in K.
No, sorry, d to the brackets 3k.
D to the, it's 3K. Oh, D to the power of 3K.
D to the power of 3k, yeah. Wait, have I got that right? Yeah. Yeah.
I see. But it looks like N doesn't get messy with D or K.
Yeah, exactly.
But then I guess one of the challenges then is if it's like an image data, for example, the ambient dimension is pretty big. So that's one of the bottlenecks.
It would be, although so the D, you only need to have an embedding into RD. So if you did dimensionality reduction first, that would be fine. So even if you only reduced it to like 10 dimensions and then did it, that would still be fine, and you would still be estimating.
I see. So you can more or less so if there's intrinsic dimension, you can reduce it to like say 2D by I don't know, Whitney embedding, but
Yeah,
exactly. But okay, I see what you mean. Thank you.
Yeah, but the crucial thing there is that's not the same as doing dimensionality reduction as a pre-processing step and then doing this in the lower dimension. You're still estimating it in the high dimension, but you've just represented forms via this lower dimensional thing, which maybe we should talk more about another time. But yeah, it's not just that you pre-process first and then compute this. You're still estimating the high dimensional thing just more efficiently.
Oh, okay. I think we can talk about another time.
Yeah.
Okay, more questions?
Shall I answer the one?
In the chat, Sarah.
Oh, is there sorry. Yeah, I apologize. You showed some examples of robustness, but are there any formal guarantees of stability? For example, if you have two similar Laplacians, do the various geometric objects you construct from them satisfy some kind of dissimilarity bound or inequality in terms of the dissimilarity between the Laplacians?
I feel like I should have a better answer for this than I do, other than it definitely is stable, because when you play around with it, it kind of obviously is. I feel like I'm sorry not to have a sort of clearer answer than that. I think if you like in the end, like you're basically just multiplying a load of matrices and tensors, and that's stable. And so if you move your points around a bit, you'll get a slightly different Laplacian, and then when you multiply it out, you'll get a slightly different thing. So I should probably think of how to formalize it, but basically you make a matrix in a continuous way, and then I mean it's not only continuous, it's all differentiable. Like it's all, you make a matrix in a differentiable way, and then you multiply matrices, and then that's all you're doing. So yes, I think that's the answer.
Okay, so we have a question from Pablo.
Hi, thanks for the talk. It was very interesting. Look forward to reading your papers more. But
Cool.
in the metric measure space area where there's been a lot of development in these RCD-KN spaces.
Yeah.
So in there's this notion of convexity of the entropy functionals in order to get lower bounds for the analogous of the Ricci curvature. So in relation to that, like how do you see the diffusion geometry perspective fitting into all of that theory, and how, because in there you kind of have to assume or have a hypothesis that you have this convexity of several entropies, either relative or Rényi, and in here you kind of don't ask for that. You just start off saying we're going to use a Carré-Duchamp and we're going to define everything. So could you comment on how you see those two things working together, I guess?
Yes, absolutely. That's a great question. Thank you. When saying like the Nicola-Gigli theory on metric measure spaces, they are explicitly constructing stuff involving the using the RCD condition, which guarantees regularity of, like, it guarantees the existence of the Hessian for like a suitable class of stuff, which you need in order to show that you're like when you do higher order calculus stuff, that is all well behaved. And an analogous thing is true here. Like if you have the associated Bakry-Emery lower bounds on Ricci curvature, then you can show similar sorts of stuff, although this is something that I'm currently working on separately. I think in terms of how the two theories generally fit in, if you have a metric measure space, you can use it to make a Carré-Duchamp. And then if you do diffusion geometry with that Carré-Duchamp, you would get an equivalent theory. So you can realize the metric measure space theory as a special case of this, in the case that the Carré-Duchamp that you get is one that arises from the Cheeger energy that you construct with the metric and the measure. But I think the really important point with this is that what you need in order to do the geometry is the energy function, like the Dirichlet energy or the Cheeger energy and the Carré-Duchamp. You don't really need the measure. Sorry, you don't really need the metric. So even though metric measure spaces are a source of Dirichlet energy from which you could do this, they aren't all of them. So there's this property called tau upper-regularity of energy functional that the tau upper-regular energy functions are exactly the ones that arise from metric measure spaces, but not all of them do. So you can do this in a more general setting where you have a measure space and energy functional that isn't tau upper-regular. That's one that couldn't have arisen from a metric measure space, but where you can still do this. And sort of to go the other way as well, a ton of different metrics would give you the same geometry. Like, because you only really care about the derivatives, you can like arbitrarily deform the large values of the metric and you haven't changed the geometry at all. So in a way, like, even though the metric is a source of geometry, it's kind of not the point, because what you really care about is the Carré-Duchamp information that you obtain from differentiation. And so like the map from metric measure spaces to geometries it's sort of neither injective nor surjective. Like tons of different metrics would give you the same geometry, and also not all of the geometries arise from metric measure spaces. So that's kind of how they fit in.
Great, thanks. That's a very interesting question. Yeah. Thank you very much. It's great talk.
I'm definitely like I'm like halfway through working on this as well, and I'm really looking forward to like actually stamping out exactly what the relationship is, because I think there's tons of interesting questions there. I don't know if there are any interesting examples that aren't metric measure spaces, but yeah, but it's still more general. And I think for me, the point is that it's quite clean. Like you can have a metric and you can use that to do the geometry, but that isn't really the point. The point is that you can get a carré de champ, and that's the thing that gives you the geometry. And you can like strip out the metric after like page 2 of your theory if you go to the carré de champ, and then you never need to think again about the fact that that's where it came from, because it isn't really essential.
Yeah, I guess
Perfect.
I'd have to look more into this Bakry-Emery condition that you used as well, because that does appear in this other RCD and metric measure space here. So maybe that's like a starting point to consider.
Yeah, exactly. There's the Invenciones paper from like 2014 or something where they show that they're equivalent.
Yeah.
That's
Okay, wonderful. So thank you so much for the wonderful talk. I'm going to stop the recording here, and then whatever further questions we have, we're going to take them offline. And see you all next week.